Hey guys, Catlin here with your cool down help for 8th grade math. I'm going to knock out 2 videos with this one, and it probably would be helpful if I brought my microphone over here. I'm going to knock out 2 videos with this one. I'm going to do lesson 8 and lesson 9 since we kind of combined those with our lessons in class today. So lesson 8 was about similar triangles, similarity with angles, and then today's lesson was about side length quotients in similar triangles. So we're going to kind of do the same thing in both of these. If we want to prove that these two triangles are similar to each other, all we have to do is make a table and prove that they have the same constant of proportionality. So, or the same scale factor, so to speak. So I'm going to make a little table. I got my small triangle on the left, which is over here. I got my bigger triangle on the right? Smaller, bigger. And we're going to put some corresponding sides into the table to test to see if there's a scale factor. So let's go to the sides that we know. We know this one's 3. We know that this one's 4. We know that this one's 4, but we don't really know where this one stops. So we can't say it's 5.5 for sure, but it looks like it's close to 5.5. It's kind of a mystery to us right now. But we know in the smaller one, the 3 side on the bottom corresponds with the 4 side in the larger. And we all know that the 4 side in the smaller one corresponds with the question mark in the other. And what would help us know if these were similar is if we had a constant of proportionality that would get us from one side to the other and prove that this is 5 and some change. And then we feel a lot more confident about them being similar. I mean, they got the same angles, it appears, but if we could prove that they have the same scale factor, then we really know that they're similar. So to find a scale factor in a table like this, you take a pair that are across the table from each other, and you simply divide them. So all we're going to do is 4 divided by 3, and that gives us our scale factor. We don't even have to actually do the division. We could literally just write 4 multiplied by 3 there. And for some reason, my pen stopped working. So I'm going to do my best to make this work. Multiplied by 4. I'm going to use my mouse. It's not going to be as good, but oh well. Not really sure why that happened. Maybe my battery died on me there. Let me turn it back on and try it again. Sorry, there we go. Okay, so 4/3 is my constant of proportionality that gets me over. Now, does that work for 4 times 4/3 to get the unknown mystery number here? Let's try it out. 4 over 1 times 4/3, which is our constant of proportionality that we found by dividing the two numbers that corresponded. That gives us 16 in the numerator and 3 in the denominator. Now, 3 will go into 16 a nice whole 5 times because 5 times 3 is 15 with 1 left over. Does this look like it is at 5 1/3 of the way up to 6? It sure does. It sure does. So I feel really confident that these are similar, and I feel like my shown work over here proves with my shown work that they are similar to each other with a constant of 4/3. So if 4/3 is my constant that gets me from small to big, it is also known as my scale factor to get from ABC to ABC prime. And so my scale factor is also 4/3. All right, let's jump on down to the last one. Lesson 9. I'm putting this one on there too just because it really falls in with what we talked about today. 2 triangles are shown to be similar, smaller and the larger one here. And the value that we're trying to find here is A to B. So we're trying to find the ratio of A to B. Now, because these are similar, A to B should be equivalent to 21 or 2.1, to 1.4. Now, I say 21 because in my mind, when I have 1 decimal points like that, I like to go ahead and just multiply them both by 10 and think of it as 21 is to 14, which is a much easier way to simplify than trying to simplify this as 2.1 and keeping it in that respective. So I'm going to divide both of these by their common factor, which in this case is 7. And when I divide them both by 7, I get 3 in the numerator and I get 2 in the denominator. So this says that my ratio of A to B, since my A is longer and my other side is shorter, this is a 3 to 2 ratio. So 3 to 2 is what A to B is equal to. I should be 3 parts A to 2 parts B. And that makes sense because if I split this up into 2 parts, that length seems to make 3 on the A, right? It would take 1, 2, 3 of those parts and only 2 of those parts along B. So it's a 3-part to 2-part ratio. And you can do the same thing down here. I split this up into 1 part, 2 parts, and then that length right there, which appears to be about that long, would take 3 parts on this side. It's always going to be a 3-part to 2-part ratio, even as those parts grow in size or shrink in size. It's always going to keep that ratio of 3 parts to 2 parts. And that's what we're doing with these similar triangles. See you guys.